Hi, welcome to part 2 of our discussion on Earth's motions. Today's focus is going to be Earth's revolution and the effects of that revolution. When we say revolution, what we mean is the movement of an object around another object. So it could be the Earth around the Sun, as we'll stress today, or it could be the Moon around the Earth, or really anything that's orbiting something else. When we talk revolution, a lot of times it's helpful to know the revolution's period. The word period references the amount of time it takes to revolve. Of course, for Earth, the amount of time it takes to revolve is what we measure a year. As you probably know, it takes 365.26 days for the Earth to orbit the Sun, and so that is the length of our year. The 0.26 days is why every 4 years we add an extra day in leap year to make up for that quarter of a day. We call the Earth's orbit the ecliptic. We've mentioned the ecliptic already as the path of the Sun through the celestial sphere. Well, if you imagine yourself removed from our solar system and you were looking down at it, the plane of the Earth's orbit would also be the ecliptic because one is from Earth's perspective and the other is from space's perspective. So there are a couple of main effects that revolution has on our experience on Earth. The first effect is that revolution causes the visible constellations to vary. Recall that some stars and constellations are considered circumpolar. Remember, that means that they're visible all night long. Well, because the Earth's tilt doesn't change, they're visible all year round, too. The circumpolar stars and constellations are the ones that are closest to the celestial poles. Remember, they appear to be orbiting around the celestial pole, and these are the ones whose orbit never dips below the horizon. And so they have higher declinations, in other words, closer to the celestial poles. In this diagram, the yellow would be circumpolar. The pink would be the stars that aren't visible at this latitude. The rest of the stars, the ones in white, are the ones that we consider seasonal. In other words, we can view them at some point during the year, but not all year. Remember, which stars are circumpolars vary with your latitude, and therefore which stars are seasonal also vary with your latitude. In general, though, the stars that are lower in declination, in other words, nearer to the ecliptic and the celestial equator, are the ones that are going to be seasonal. To help you better understand why this is, let's look at circumpolar stars first. So here we have a picture of the Earth's orbit. Remember, its path is the ecliptic, so this line on the outside would be the ecliptic. And in this diagram, the side of the Earth that is facing the Sun is the side, of course, that's lit. If you're facing the sunlight is so bright, it's scattered by our atmosphere, you can't see any other stars because the sun's light is going to block all of them out. However, stars that are above the celestial poles, such as Ursa Minor, are going to be always visible because they're never going to be in the same direction as the sun. The sun's going to be on the horizontal plane and these stars are up and down. Seasonal constellations are going to be the opposite. They're going to be on the same plane as the sun, not just left and right as I identified here, but also towards the screen and behind the screen. So if we imagine this picture and that this location is summer, then that means during summer, the stars that are in this direction are in the direction of the sun, and so consequently, you're not going to be able to see them because the sun's light is going to block it out. So you'll be able to see this at night. This constellation is Scorpius, but Orion, which is on the other side of the sun, is not going to be visible. Conversely, 6 months later in the winter position, now Orion will be fully visible because it's in the nighttime direction, whereas the stars towards the sun are going to be those that we could see in summer. Now we can't, such as Scorpius. For most latitudes, there's a lot of seasonal constellations because there's a lot of constellations that are in the same general direction as the sun. However, there are certain constellations that are in the exact direction of the sun. We call those constellations zodiac constellations. So, zodiac constellations are the constellations that are on the plane of the ecliptic. Another way of thinking about that is they're the ones who appear to be directly behind the sun. You might have heard the phrase, "What's your sign?" For people who believe in astrology, they believe that the position of the sun on your birth date has something to do with your life. Quick side note, astrology is not a science. There's no evidence to support it. We'll talk more about this in class. But for many people who get kicks out of checking their horoscopes or using "What's your sign?" as a pickup line, most people like to know what their sign is. Here's how it works. Let's use a couple of birthdays as examples. My nephew was born on August 27th, So on his birthday, the sun was about here on its orbit. So on that date, if you looked at the sun, directly behind there would be the constellation Leo. So his sign is Leo. I was born on December 17th, so the Earth would have been about here. On my birthday, looking at the sun, directly behind there is the constellation Ophiuchus. The biggest effect that revolution has is, of course, our seasons. So when we refer to seasons, what we mean is the changes in local climate that are caused by the Earth's revolution combined with the Earth's tilt. As the Earth orbits the sun, it orbits the sun always tilted on an axis of 23.5 degrees. In other words, if the plane of the ecliptic is here, the Earth's orbit is not straight up and down, it's on an angle. That angle is about 23.5 degrees, and it's a constant angle, so it's always 23.5 degrees. Not only is the amount of tilt constant, but so is the direction. As the Earth orbits the sun, notice in this diagram that the Earth is always tilted up and down. In other words, in this animation, up and to the left. On one side of the Earth's orbit, the North Pole is tilted towards the sun. In this diagram, it would be tilted towards the right. On the other side of orbit, it's still tilted in that same direction. It's still tilted up and to the right in this diagram, and that's going to make the North Pole pointing away from the sun. The constant tilt combined with the revolution of the Earth has several effects, and the first of which is where the plane of the ecliptic intersects Earth. So the plane of the ecliptic, remember that's Earth's orbit as well as where the sun appears to be from our perspective. The plane of the ecliptic also represents the part of the Earth that is getting the most direct sunlight. That, of course, also means the most intense sunlight. At that location, the sun will be directly overhead, and only at that location. The latitude of the ecliptic varies throughout the year because of the orientation changes as it orbits the sun. When the Earth is tilted towards the sun, we see that the plane of the ecliptic intersects above the equator. So here's the equator, and here's where the ecliptic intersects it. We call that latitude the Tropic of Cancer, and it's as far north as the ecliptic ever will be. Conversely, when the North Pole is tilted away from the sun as it is on the left, we see that the plane of the ecliptic intersects below the equator. That latitude is referred to as the Tropic of Capricorn, or in other words, the southernmost latitude. It is only in between these two places, the Tropic of Cancer and the Tropic of Capricorn, that will ever experience the sun directly overhead. The changing location of the ecliptic therefore affects the altitude at transit. So recall that the transit is the position of the sun at its peak. Remember, this occurs around noon depending upon location. Take a look. If the North Pole was tilted away from the sun, as it is in this picture on the left, then here in Wisconsin, which would be about here, when we look at the sun, we'd be looking at a very low angle. It'd be very low in our sky. This angle right here is very, very small. Conversely, if the North Pole is tilted towards the sun, Wisconsin would be about here, and our angle of the sun is a much higher angle. In other words, the angle off the horizon would be much, much greater. As we see throughout the year, depending upon where the ecliptic is hitting the Earth, will affect how high in the sky the sun appears to be. In the summer, the sun will appear the highest, and in the winter, the sun will appear the lowest. In this diagram, the ecliptic is coming from right about here. As you can see, the angle from the northern hemisphere would be very low. However, at the North Pole, the angle is so low that it's below the horizon. We call this a polar night. So anything inside the Arctic Circle, which is 66.5 degrees of latitude, is going to experience some form of polar night for at least some time. If it's exactly at the North Pole, it will literally be all of winter. If it's lower, it will be a shorter portion of that time. So a polar night is when the sun never rises because it's in this section of the sky. So as this Earth rotates, it never rotates into the portion of daylight. Conversely, in the South Pole, they're experiencing a midnight sun. In other words, as it rotates, the tilt of the Earth is causing the sun never to appear to set because it never spins out of the daylight. If you were near the poles, it might look something like this for a midnight sun. whereas this time of day might literally be midnight. This location would probably be very, very north, although not right at the North Pole. This would be a little bit further south, but still within the Arctic Circle. And as midnight rolls around, the sun would get very low on the sky, and there would be a prolonged sunset, but it would never actually set. The altitude of the sun can also be used to tell what time of year it is. So because the altitude of the sun changes with year, and because the constellations that are visible changes throughout the revolution of the Earth, we can use that as a calendar, and in fact, many ancient cultures did. So what we're talking about is seasons. So when we think of seasons, we think of either being warm in summer or cold in winter. But what actually causes that temperature difference? Many people falsely believe that because the northern hemisphere is tilted towards the sun in summer, that makes the northern hemisphere closer. That is true. It is closer than the southern hemisphere in summer, in July. However, it is not closer than winter. In actuality, the entire Earth is 5 million kilometers closer to the sun in winter than it is in summer. So whether there's a couple of thousand kilometers difference between when the Earth is tilted this way versus that way makes no difference when we're talking about a difference of 1 million miles of the whole planet. So if it's not distance that's causing the seasonal changes, what is causing those changes? Seasonal temperature differences can be attributed to two main factors: the intensity of the sunlight as well as the duration of sunlight. I like to use the analogy of cooking something in an oven. When you cook, recipes give you a time and a temperature to cook something at. If it's not in the oven long enough, or if it's not hot enough, what you're cooking won't cook. Basically the same is true for the Earth. Our temperature on Earth is affected by how long our sunlight is and how intense that sunlight is. Generally, the higher in the sky the sun is, the warmer it will be. This is because of the angle of sunlight. The altitude of the sun affects the intensity of the sunlight because it affects how spread out the light is. When the sun is hitting the Earth straight on, as it is here at a 90-degree angle, and here with a flashlight, just like you saw in lab, the sunlight is concentrated in a smaller area. But when the sun is lower in the sky, the sun is at a lower angle, and that same amount of energy is spread out over a larger distance, and so it's less intense. Additionally, the rate that the Earth rotates doesn't change, so if the sun is at a higher altitude, it's going to take longer for the sun to travel its path than when it's at a lower altitude. So that means longer days and more time for the Earth to get warm. As the Earth orbits the sun, there are 4 particular locations that we have special names for. They're called the solstices and the equinoxes. These are both the location in our orbit as well as the date in our orbit and a specific time when the Earth's tilt is either tilted towards, away, or perpendicularly to the sun. The first we'll discuss is the summer solstice. Solstice comes from words that mean sun and stop. In other words, the altitude of the sun stops moving northward on the summer solstice. It's the furthest north it's going to be. And this occurs around June 21st, give or take a day or two. And it's when the northern hemisphere is pointed towards the sun. At that time, the sun is intersecting the Earth at the Tropic of Cancer. And there's a high angle of sunlight in the northern hemisphere. That high angle means the sun reaches a higher altitude, and therefore there are longer days. And since the sun is at its northmost position, the sun rises and sets north of due east and west. On June 21st in the southern hemisphere, the North Pole is still pointed towards the sun because it applies to the entire Earth. However, because they're in the southern hemisphere, they have the opposite conditions. So the sun is at a low angle, there are short days, and obviously it's cold. Conversely, the winter solstice occurs in December, around the 21st. At that time, the northern hemisphere is tilted away from the sun, and the southern hemisphere is tilted towards it. Consequently, the ecliptic is intersecting the Earth at its southernmost point, the Tropic of Capricorn. And for us in the northern hemisphere, we have a very low angle of sunlight because the sun is at a very low altitude. That corresponds to short days, and the sun rising and setting south of due east and west. And once again, this would be the opposite. In the southern hemisphere, they would experience angle of sunlight that's very high with long days and warm temperatures. Finally, we have equinoxes. The equinox literally means equal night. Those occur September 21st and March 20th, and they represent the days when both hemispheres are pointing perpendicularly to the sun. In other words, the tilt of the Earth is not tilted towards or away, but the sun's in one direction and the tilt is in 90-degree different direction. On those days, since neither hemisphere is tilted towards or away from the sun, the ecliptic is hitting at the equator. That represents a medium angle and medium altitude of sunlight and equal hours of daylight. Remember, equinoxes mean equal night, so there's exactly 12 hours of daylight and 12 hours of nighttime. On those days, the sun should rise due east and set in the due west. On the vernal equinox, that represents spring. In other words, when the sun is moving northwards with each day, or in other words, towards the summer location in its orbit. Recall that the vernal equinox was our basis for measuring right ascension. What that means is when the Earth is in the location where the vernal equinox occurs, that is the direction of zero right ascension. The autumnal equinox is when the Earth is in the fall position, in other words, heading towards winter, and the sun is moving southwards with each passing day. You have a diagram like this in your notes. The 4 positions of Earth represents the solstice and equinox positions in our orbit. Notice in all 4 positions, the tilt is always pointed in the same direction. In this diagram, we're going to represent the ecliptic using an arrow drawn straight out from the center of the sun towards the Earth. In this position, the northern hemisphere is tilted away from the sun, making this the winter solstice. If you take a second and shade in the dark area, it should become obvious that the southern hemisphere is more lit up than the northern hemisphere is. Take a second and label that the winter solstice. If you're a visual learner, it might also be a good idea to put some of the characteristics of winter in that location. 3 months later, the Earth has gone a quarter of the way around its orbit. Draw an arrow to represent the most direct sunlight. It should hit directly at the equator. Notice there's nothing to shade because in this perspective, the dark side of the Earth is facing the back of the screen. And you should know that both hemispheres are being equally lit by the sun, so they're receiving equal amounts of sunlight, and this represents the vernal equinox. 3 months after that, we have the summer solstice. Note, the tilt of the northern hemisphere is towards the sun, and the ecliptic and most direct sunlight is hitting north of the equator. If you shade in the light and dark areas, it should become obvious that the northern hemisphere is far more lit than the southern hemisphere. And consequently, the northern hemisphere is receiving more light. Take a moment and label that summer solstice. Finally, the last position is the autumnal equinox. The ecliptic is hitting once again directly at the equator. This time, from this perspective, the part of the Earth that's in this diagram would be completely shaded, and notice that it's the entire Earth, north and southern hemisphere, that is shaded, where the opposite side would be entirely lit. So both hemispheres are getting equal sunlights and therefore equal energies. Once again, label this the autumnal equinox. That's it for this video. The last little bit of your notes on precession we'll cover in class. As always, come see me if you have any questions.